So, hi, I'm Josh. I'm from the University of Cambridge, and today we're talking about experimental investigation of relative humidity on particle charging. So, just a brief bit about particle charging. It's used ubiquitously throughout aerosol science to bring particles to a known repeatable charge distribution. And there's three types that are mainly used for particles less than a micron in size. Bipolar charging, which is the most commonly used, where a particle is subject to both positive and negative ions, and it contains a steady state charge distribution, which is invariant in time. Unipolar charging, which is where a particle is subject to ions of a single polarity. And you can keep increasing the charge state on this particle, which is good for signal to noise ratio. And then finally, which is the less commonly used method, is photoelectric charging. And the reason it's less commonly used is because it's very sensitive to the material of the particle you use, unlike bipolar charging and unipolar charging. But a particle will absorb a photon, eject an electron, become positively charged, and then that electron is removed from the flow using an electric field. So how is that implemented in aerosol measurement? So regardless of the measurement, whether it's size resolved, so we're trying to get a size distribution out, or we're trying to get some average particle characteristics such as number concentration or particle surface, we want to bring the aerosol to a known repeatable charge distribution. And it's important that it's known and repeatable, so that when we get our raw data and we invert it, we need to know the charge fractions. For instance, for a scanning ability particle size, we need to know the charge fractions a priori, or otherwise we'll get the incorrect size distribution out. And it's the same for low-cost measurement devices where we have a charge or an ion trap and an electrometer, so that measures the integrated charge essentially. We still need a repeatable charge distribution so that when we take our current, we can relate it correctly to the particle metric we're interested in. And why we've looked at humidity is that all these different types of measurements are used in lots of different ambient environments. And so we want to know whether humidity had any effect. And it's really often suggested that when you take ambient measurements, you should dry the aerosol before you take that measurement so that the charge distribution is repeatable. But recent studies have shown, specifically for the scanning ability particle size, that in humid environments, it tends to overestimate the number concentration. So how are we going about investigating this? Well, we've generated an aerosol. And so for both unipolar and bipolar charging, we looked at DOS, which is an oil-based liquid aerosol. For photoelectric charging, we looked at nigrosin, which is a black dye soluble in water, and silver particles. But regardless of the aerosol, we size selected it using the aerodynamic aerosol classifier, which gives you a monodisperse distribution in aerodynamic space. And if the particle is spherical, that's also monodisperse in mobility space. And then it's gone through an electrostatic precipitator. And with that, we've removed any charged particles that might exist due to the generation process. And then that's gone into a mixing chamber, mid-mix with a combination of silica, dried air, and humid air put through a bubbler. And from that, we have a monodispersed neutral humidity controlled aerosol. So with that aerosol, we've then sampled in tandem with a CPC to measure total number concentration. Any excess flow has gone through a humidity sensor to measure the humidity that's at the inlet of the charger. And then this here is the charger essentially. So we looked at three different candidate chargers. The TSI neutralizer, the LP corona charger, which is a positive unipolar charger, and then a UV photocharger developed by Nishira et al. And so the aerosol goes through the candidate charger. We remove any excess ions that might exit the charger, which interfere with the current measurement, and we measure the total current on the aerosol. And with the CPC and the electrometer measurement, we can measure the mean charge on the aerosol. Any uncertainty that I'm going to show in the following results is got through propagation of uncertainty, where we assumed a 1 femto uncertainty in the current, 5% uncertainty in the number concentration, and 1% uncertainty in the flow rate. And the results are for between 10 to 60% humidity. Now we have taken data at 70 to 80% humidity, but I recently found some literature that suggests that the electrometer you use, which is TSI 3068B, may exhibit drift above 60% humidity, so I've opted to not include that. So the first charge we looked at was the TSI krypton neutralizer. So first thing to note is that the mean charge is negative, and the reason it's negative is, so I refer to this equation up here, is that the negative ion is more mobile than the positive ion. So the net charge distribution is slightly net negative. And this is the graph of humidity on the x-axis against mean charge on the y-axis for 3 different characteristic diameters. And as the humidity increases, we can see that the mean charge increases as well, so it gets more positive. And if using that equation, that would suggest that Z plus over Z minus, which is the ratio of ion mobilities, increases with humidity, which means that the positive ion mobility is becoming closer in value to the negative ion mobility. And measurements we've performed with a high resolution DMA, as well as other measurements of ions using using a high res DMA in literature, show that there is a significant difference in the mobility distribution that you get in dry air compared to ambient or humid air for a bipolar charge, which is the cause of this increase in mean charge. The second charger, the photoelectric charger. So we've investigated 2 types of particles here. So the blue and red lines here are nigrosin, which is a hydrophilic material, and then silver, which is hydrophobic. And the overall trend is that as humidity increases, the mean charge decreases. And there's a slide after this, which is essentially a bit clearer than that graph. But possible reasons, if I could refer to this equation up here, which is an approximation for the mean charge. It can vary due to the intensity of the light, the work function of the material, which is Y, and then sigma PC, which is the photoelectrically active surface area. And that can change if water is condensed onto the particle surface. And there's a third potential reason why this mean charge is decreasing. And there's studies that have shown that water droplets can be formed in the presence of humid air with UV light. But we measured the current of those water droplets, and that was negligible. So we've ruled that out as being a direct cause to the decrease in mean charge. And so comparing either effect of attenuation UV light or coating the particle surface, it's easier to look at the graph on a normalized basis. So this is the same graph, but with everything normalized to the charge at 10%. And you can see that for different materials and different diameters, between 10 and 40% humidity, we see them collapse onto one another, which we therefore suggest means that the main cause of attenuation of decrease is attenuation of the UV light. But as we get to higher humidities, there does start to be some separation in silver, which is the yellow and purple, and nigrosin, which is blue and red. And we suggest that's potentially due to the growth of nigrosin in humid environments. The final charge we looked at is the unipolar charger, and what we have here is 2 different diameters, so 200 nanometers aerodynamic and 300 nanometers aerodynamic, and at 3 different applied voltages. So when you use a corona charger, there's a voltage at which you start producing ions, and for this LP charge, we found it to be about 3 kilovolts. And as you increase that voltage, you produce more ions within your charger. So we found for voltages far above the onset voltage, which is 3 kilovolts, so that would be 4 kilovolts and 3.5 kilovolts, which are these blue lines, green lines, and red and yellow. The response to changes in humidity is fairly flat. It's within 10% of the dry value, with potentially maybe a slight decrease. But for values at the onset voltage, which is 3 kilovolts, we see a stark increase in the mean charge per particle, so going from effectively 0 and for a 300 nanometer particle all the way up to 4 at 60% humidity. And really the only reason that can be is because there are more ions present within the charger. And if I just compare to other results in the literature, so this is results by Uruti et al., who measured discharge current, and discharge current can be thought of as a proxy for the number concentration of ions within a charger. So for voltages far above the onset voltage, so for their charger it's 2.5 kilovolts, we have a fairly flat line here in terms of discharge current, which means that the ion concentration is fairly constant within the charger with humidity, which is similar to our results here for mean charge per particle. However, at at the onset voltage, you see these steep increase in discharge current, which is, like I said, a proxy for ion concentration, meaning that the ion concentration is increasing for those low voltages as the humidity increases, which is the same as we see here for our for the LP charger. So in conclusion, if we just take the three chargers separately, the bipolar charger is sensitive to humidity changes due to the sensitivity of the ion mobility distribution, changing for both positive and negative ions. The photoelectric charger, we were saying that the likely cause is attenuation of the UV light, but there is some effect of condensed water vapor onto the particle. And then for the unipolar charger, if you're far above the onset voltage, there's not really an effect, but when you're close to the onset voltage, you see this steep increase in the mean charge of particle. And what that means is that researchers using charging in methods in ambient conditions should really report their relative humidity values, so they're not making any erroneous conclusions about their measurements. Thanks for listening. Any questions?